Hello and welcome to another edition of Standard Motor Products Power Hour. Today's topic is going to be air conditioning best practices. And without further ado, we are going to get underway. Our topics today, we're going to talk about how original compressors fail. You know, you've got a vehicle in the shop that's got a bad compressor. You know, it's important to understand what led to that circumstance so they can be sure that you correct that in the repair. We're also going to look a little bit at root cause identification, you know, trying to identify why did the compressor fail, and then what do I need to do to ensure a comeback-free repair that blows ice-cold air and keeps my customer happy. We will also talk about some few quick service tips, and we're going to wrap it up with some new compressor technology. So just FYI, I'm sure you know this already, but you know, if you work on air conditioning for profit or even to buy refrigerant in containers larger than 2 pounds, you do need to be Section 609 certified. And if you want to get certified, I think the fee currently is about mobileairclimate.org, and you know there's a Section 609 tab, and you can take it from there to get certified. If you work on cars and light trucks, you need to be Section 609 certified. If you work on planes and trains and some of the types of equipment in the right column there, there's another certification called Section 608. That's what you would need to be certified on there. So not going to get too deep in the weeds here, but it is important to kind of understand some air conditioning basic principles. If I take a tank of R134A there on the left or R1234YF on the right, you see that if I was to cool that tank to 34 degrees, let's say, the static pressure in the tank of 134A would be about 29.5 psi. Whereas in a tank of R1234F, the pressure would be about 32.9, about 33 psi. The point I'm making here is if I was to draw refrigerant off the top of either of those tanks, the pressure is going to drop. And what's going to happen is the refrigerant is going to evaporate. The refrigerant will start evaporating until it reaches that, what we call the saturated pressure temperature. It will evaporate until it, you know, at 34 degrees, it gets back to 29.5 psi. So if I put a refrigerant, if I charge a system with refrigerant, and you can see here I've got the compressor in the top middle there, and I've got an expansion device on the bottom toward the left, evaporate on the right, evaporate on the left, condenser on the right. If I start the compressor off and I start drawing refrigerant out of the evaporator, and I reduce that pressure, let's say to 30, somewhere between 25 and 45 psi on average, right? That refrigerant in the evaporator, any liquid refrigerant in the evaporator will start to boil or evaporate. And now the compressor is going to pump it into the condenser. It's going to force it up against the restriction of the expansion device, the TXV at the orifice tube. That's going to raise the pressure and the temperature. And if I turn the fan on and blow air across the condenser, it's going to condense back to a liquid. And that liquid will be forced up against the orifice tube or the TXV. And then, of course, the compressor, either using the TXV or sighting the compressor, and control the pressure on the liquid in the evaporator so that it keeps boiling, let's say, somewhere between 35 and 40 degrees, something in that range. So just with that little bit of information in mind, let's think about how original compressors fail. The first concept we want to understand here is latent heat of evaporation. So if you look at in the graph here, you see the bottom axis is energy input, or BTUs, British thermal units, and the left axis, of course, is temperature. So if I add a little temperature to the refrigerant, the liquid is going to start getting warmer. But if I've got it in that pressure range, 25 to 45 inside the evaporator, you can see that as I add energy, that phase change, that's when the refrigerant is actually evaporating. You can see that as I add energy here, there is no increase in temperature. In other words, as the refrigerant is boiling or changing state or evaporating, there's no increase in temperature of the refrigerant inside the evaporator. And ideally, this is a normally charged evaporator, orifice tube type system. You can see the refrigerant is going in at 35 on the bottom. and it's coming out at 35, the same temperature on the top. And, so this evaporator, if it was a glass evaporator, I could see through it. You would see that the refrigerant is burbling, gurgling, boiling inside the evaporator, mostly gaseous coming out the top. On an orifice tube system, there will be a little bit of liquid to carry my oil up and out. But the key thing to understand here, looking at the graph, do you see that the greater amount of heat energy is absorbed as the refrigerant changes state from a liquid to a gas, but there is no increase in temperature. And that's what you want inside the evaporator, is that constant boiling state with the evaporator almost full of liquid. So now look what happens when, the vehicle is aging, the customer hasn't serviced it. Now the liquid level in the evaporator, the blue shaded area, you see that the liquid level in the evaporator is much lower now. And so what happens here is all the liquid boils away much more quickly. And so you see that the phase change, the period of phase change, is much less energy is being absorbed here during the phase change. As in other words, as the refrigerant is evaporating, because there's much less liquid, there's not nearly as much heat energy being absorbed. And the key thing you may notice here is that the refrigerant is still going in at about 35 degrees, but the pure gaseous refrigerant coming out the top is actually up around 50 degrees. And that's important, because I've got a 15-degree increase here across the evaporator. That tells me that temperature difference is a giveaway clue that all the liquid refrigerant has boiled away, and all I'm left, the liquid refrigerant has boiled away, and all that's coming out the top is pure gaseous refrigerant. And why that's important is because oil will remain more or less in the liquid state throughout the refrigerant circuit. As the liquid refrigerant boils away, the oil starts to drop out and it's left behind in the evaporator. And so as the vehicle, as over time, as the compressor wears and ages, all the lubricating film gets stripped off the evaporator, off the compressor pistons and cylinder walls, and then you get metal on metal. And over a long period of time, you can get fine microscopic abrasive particulates sloughing off the pistons and cylinder walls. That debris gets carried throughout the system. It's fine, it's microscopic, it will fit through most of the filters and screens throughout the system, and it will be concentrated, typically because of that oil that's been pooling in the bottom of the evaporator. That abrasive soup will be concentrated in the bottom of the evaporator. So you can appreciate, therefore, this is the typical failure profile of how most original compressors fail. And typically when the original compressor fails, you'll have a dirty abrasive soup of oil and abrasive debris in the bottom of the evaporator. And you can appreciate and understand that would be important to get that out of there. So compounding the issue, if we look back to the original R12 systems, R12 and mineral oil, the oil we used back then, the molecules of oil and refrigerant kind of had an attraction for each other. So even when the evaporator was low on liquid refrigerant, as the refrigerant evaporated, because the molecules were attached to each other, the evaporating refrigerant carried oil with it up and out of the evaporator. And so you maintained compressor lubrication even with a low charge on an R12 system. However, on an R134A system, maintaining lubrication is much more difficult. And that's because as the liquid level drops in the evaporator, as the refrigerant evaporates, there's not nearly the same molecular attraction between the refrigerant molecule and the PAG oil molecule. And so the oil gets left behind. And of course, inevitably, the compressor fails. This is the end result. This is, I would say, 80% of original compressor failures. This is what results. This narrative, this sequence of events is what typically results in the original compressor failing. So as you might have noticed from the slide there, the excessive superheating in the evaporator, by measuring temperature differences throughout the system, you can make very strong diagnostic. You can get a strong diagnostic sense of what may be wrong with the system. We're not going to get too deep into it today, but if you want to find out more about temperature testing, go to our website, 4s.com, click on the Technician Resources tab, and you will see over there there's a maximum heat load temperature testing. Some people call it differential temperature testing. It's a very detailed document explaining how you can use temperature testing to get powerful diagnostic insight into what's going on in an air conditioning system if it's not performing the way you would expect, or you're having repeat compressor failures. There's some great information here on the website. So let's look then at what are some of these essential steps that we need to follow to ensure successful compressor replacement. So the first caution I would add here is that every inch of the refrigerant path should be either new or flushed. And that includes every single component: the condenser, the evaporator, the dryer, the expansion device, the hose assembly. Some of those components must be new, as we will discuss in a moment, but every single one of those components should be either new or flush. The system should be charged with the exact amount of refrigerant. We'll come back to that later. The correct type, amount, and viscosity of oil, and proper condenser airflow. You see, I've capitalized that because you'll be amazed at the number of air conditioning performance problems that can be traced back to a condenser airflow issue. So I'm kind of emphasizing that. And of course, keeping in mind that low charge is lack of lubrication, it's important that we do a thorough leak check, ideally before we do the repair, and then again after it, before we turn it back to the customer. So let's talk a little bit here. I've got demonstration set up here. Let's talk about how we're going to identify the root cause of the compressor failure. So I have here a compressor, and it's off of an older truck. And the first thing I'm going to want to do is I want to do an old oil analysis. I want to figure out, using the old oil, I can figure out a lot about what actually caused this compressor to fail. So the first thing I'm going to do is, if I try to drain the oil from the old compressor, there's a little bit coming out here. So you can see that I'm getting very little oil out of this compressor. And why that's important is this. Let's suppose it was a 7 or 8 ounce system. It held 8 ounces of oil, and I only get a ½ ounce out of the compressor. Right there, I know that there's 6, 7 ounces of dirty oil still somewhere in the system, and that dirty oil is almost certainly in the evaporator, and that's that it's that valve lapping compound, if you want to call it, that's going to be dropped out on the bottom of the evaporator. The other thing, of course, is I'm going to look at the condition of the oil. Here, for example, this was a repeat. This was actually a warranty return compressor. It turns out when we did an analysis, the oil here, half this oil here, is actually full of solvent. The flush solvent the system wasn't properly flushed. Here you can see, and if you want to get a good sense of this yourself back in the shop, take the oil bottle of the side of your recovery machine if it hasn't been drained in a while, and look at the bottom of the bottle. You will see that there's a film of microscopic abrasive particulates settled out on the bottom of the oil, and that's what's in the bottom of the evaporator. That's why it's so important to flush the system. Here's another couple of examples here. If I look at the bottom of the glass, you can see that microscopic debris on the bottom of that has settled out, the microscopic abrasive particulates that have settled out of the oil in the bottom of this jar here from a failed compressor. So the other thing we want to, so let's move this, we'll move this display to one side here. And we are going to look at, what are some of the things we need to do? What do I need to do to properly, I've got a failed compressor. It's come in with the failed compressor. It's either seized or it's knocking, or I know I need to replace it for some reason or other. So let us see what we need to do for a successful repair here. So here I have, the first thing we, of course, insist that you replace the accumulator. If you look inside an accumulator here, we've got one cut away. You can see it's got the desiccant material in here. If flush solvent were to contact this, the desiccant medium actually gets hot, I've seen with some solvents, and it will expand. It just turns into a mess, basically. The other thing, when you look at inside an accumulator, it's got kind of a snorkel tube coming to the top here. We call this the U-tube. And you can see that if I get solvent in here, I could never get it out. You're just never going to be able to get it out. So you can't flush an accumulator. That's why it needs to be replaced. And for much the same reasons, here's a cutaway of an older style receiver dryer. You can see it's got a filter inside. It will also have the desiccant medium inside. You got to replace this. You got to replace that as well. And of course, the orifice tube. So here we have a lot of later model vehicles now are using what we call captured orifice tubes. On this one here, we've actually cut it apart, and you can see that there is the orifice tube is encapsulated in the liquid line. So to replace the orifice tube on this particular system, this was from a Dodge truck, I would need to replace the entire liquid line. Now, the other thing that comes up from time to time is the other question that often gets asked here is, well, what about the condenser? Do I need to replace the condenser? So I've got a condenser here cut apart so we can get a sense of what's going on inside of it. And you can see that, look at how it's dammed. All the header tanks of the condenser are dammed. And if I look inside, if you look at the tubes inside of a condenser, they're barely bigger than the thickness of the diameter of a hair. So you've got very fine tubes. The header tanks are dammed at both ends. The refrigerant must pass back and forth 3 or 4 times before it gets out the bottom as a liquid. So it's just impossible to flush a modern condenser. The other complicating factor here is that most TXV systems now, the receiver dryer is actually integral to the header tank. And of course, inside of that is the desiccant bag, and usually also some kind of a filter. So to flush this, to even think of it, you shouldn't be thinking about flushing it anyway, but even if you did consider flushing it, oftentimes you'd have to take the condenser out to get the desiccant medium out of there, to get the filter out and put the plug back in. It is, when you consider the cost of a new condenser versus the labor to do the flush, the pointlessness of doing a flush, and of course, the fact that it would probably cost you more in flush and labor than to replace the condenser in the first place. The other thing that we often get asked is about the TXV valve. Now, we do not insist that you replace the TXV valve, but it's very important that you remove the lines at the firewall. If I take a look in here, you can see that if there's any evidence of corrosion or rust or even a kind of a matte black film of debris in here, that you need to replace the TXV valve. It should be, if there's any evidence of contamination in the inlet to the liquid inlet to the TXV, you should replace it. And the other question that comes up from time to time is hoses, hose assemblies. So I've got a couple here. Remember, the car's in your shop, it's probably 8, 9, 10, 12 years old. The compressor has failed. As I say, low charge is often the reason that the compressor failed in the first place. And the micro leak that led to the low charge in the first place is often at a hose crimp. So if I look inside of a hose assembly here, you see the rubber, it's an organic compound that came out the side of a tree. Oftentimes, it shrinks, hardens, crystallizes as the vehicle ages, and you end up with the micro leak that led to the low charge, oil dropout, no lubrication, is often at a hose crimp. And so when you, again, if and oftentimes you won't be able to leak check this, especially if the compressor is leaking, it's cracked or it's busted in some form or fashion. You may not be able to check this hose, leak check this hose until you've recovered the system, flushed it, did the repair and recharge the entire system, and you're just about to give it back to the customer. You're doing your final leak check, and now you find the leak. So as I say, oftentimes, if you do the math, literally do the math for the cost of flush, the labor to do the flush, the fact that you don't know if the hose is leaking in the first place, oftentimes it just makes more sense to replace the hose assembly right from the get-go. Now, if it's a straight piece of hose, yes, you can flush it. But here's you look under the hood and you see a hose assembly that looks a little bit like this. It's got a muffler or some kind of a bubble in the line like this here. If we look inside here, what you see is this line is coming in here. It's coming up hard against the bottom of the can. And there's only a couple of pinholes in the tube inside for the refrigerant to pass through. So if you've got debris from a failed compressor in here, it's just not gonna, you can't flush it, is the point I'm trying to make. And on some of them, there may be a little some here. So you look at a line and it's got a bubble in it like this here. Look inside, oftentimes what's actually inside is a paper filter. Again, it's just pointless trying to flush it. Now, coming into a bit of a newer technology conversation, this is an internal heat exchanger. You'll find it on a lot of 2012 and up, a few 134A, but mostly R1234F vehicles. This is an internal heat exchanger. It improves the heat exchange efficiency on later model systems. And if you look inside here, you probably don't know how well you can see this, but it's a double-walled pipe, right? I'm not going to explain how it works right now, but it's a double-walled pipe. And if you have a failed compressor, oftentimes the skin, the debris will get trapped between the inner and the outer skins of the internal heat exchanger. And oftentimes you need to be aware that you may need to replace the internal heat exchanger in conjunction with the compressor replacement. Okay, so the next thing we want to talk about here is flushing. Let me just get my cart in position here. All right, so looking at the flushing situation here, you can see that for an effective flush, I need an effective flushing tool, I need an effective flushing solvent, and I really need to know how to do it. I need to really know how to go about doing a good flush. And the first thing I will say is oftentimes I walk into a shop and they have a flushing arrangement that looks a lot like this here. It's got a typical valve here. And you static charge it with an air chuck and you hold this up to the component that you're trying to flush. If this is the type of arrangement that you're using to flush, I'm quite serious, you're probably better not trying to flush at all, because the solvent gets expelled, the air expands, it runs out of momentum, and the solvent drops out inside the evaporator. And what you end up with is a dirty mess of solvent, an abrasive soup of solvent and dirty oil in the bottom of the evaporator. So what you need is a tool similar to this here. You can see it's got a universal adapter that I can connect up to the component that I'm trying to flush. And it's got a pressure gauge, it's got a control valve, and it's also got a shut-off valve here. So I would dial the pressure up to 40 PSI typically. I've got the valve closed, I connect it up to the component that I'm trying to flush. And now I could, even if it was an evaporator, particularly dirty oil, I could give it a little squirt for a second or two, let it sit 15 or 20 minutes. And now I can come back and turn the valve on, and I just keep the air pressure going. I connect it up to shop air, of course, keep the momentum going through the evaporator. That prevents solvent dropout inside the evaporator. So this is a much more effective flushing tool and technique than something like this here. The other thing, of course, is most modern vehicles now are what we call, they're using thermal expansion valves. And a challenge with a thermal expansion valve, as you can pretty much see here, is the valve is usually right in the firewall. It's halfway in, halfway out. It can be difficult to attach your flush tool to it. So what you can do there, actually, it's quite easy to do. It's very easy to adapt an old style TXV valve. You can unscrew the power valve, and in fact, I can unscrew the superheat. By the way, these things are not adjustable. They're set in the lab at the factory, so you don't want to be trying to do this in the field. But now I've taken the thing apart, and I just take a 1/2-inch drill bit. I drill out the liquid line, the liquid port on the valve at a bit of an angle, and you end up with something like this here. So you see, now I've got a simple, inexpensive flush adapter that I can attach to the evaporator. And I usually take a set of old suction and liquid line assembly from an older vehicle or a repair I did previously. They can, oftentimes you will find that they'll fit, 4 or 5 adapters will fit 80-90% of the cars that you actually work on in the shop. So this is how I go about flushing TXV system adapters. Now, just while I'm on the subject of flushing, you can see here's a scroll type compressor. They're particularly sensitive. You can see all the muck that's in here. This is a classic example of a compressor, a system that was not properly flushed before the compressor was replaced. So the next thing I want to talk about is you're replacing the thermal expansion valve, right? So if we look here, remember the thermal expansion valve is you will want to, where's my thermal expansion valve? We'll want to, if you're replacing the thermal expansion valve, you'll want to put some dum-dum tape, a thermal insulation tape on the power valve of the, that power valve should only be exposed to refrigerant temperature, refrigerant coming out of the evaporator. You don't want it exposed to underhood temperature. So it's very important that you put some thermal duct tape on the expansion valve as you're replacing it. So next piece of the conversation here, next piece of our conversation here, we're going to talk about compressor longevity. And let me move this prop out of the way here, and we'll talk about compressor lubrication. So of course, it's very important when you're working on it that you've got the proper refrigerant charge level. I will come back to that again in a couple of minutes, the importance of refrigerant charge level. correct type, the PAG, hybrid electric, mineral dependent, correct type of oil, the correct viscosity of oil, and of course the correct amount of oil. So while we're talking about oil, if you drive a nice vehicle, you probably pay a lot of attention to the type of oil, the engine oil that you use, and you probably change it every 3, 4, 5, 6, 7,000 miles, depending on the recommended interval. And a lot of science, as you probably already know, a lot of science goes into oil, oil development and oil additives and so on and so forth. Well, the oil that we use in a compressor, you're expecting it to last the life of the vehicle. Oils have all kinds of additive packages to improve various features of the oil. They're end capped so they encapsulate, keep moisture in suspension in the system so it doesn't cause corrosion and so on and so forth. We'll have antioxidant additives, ashless anti-wear, so you don't get kind of a soot buildup as the oil is temperature cycled or heat cycled in the system, metal passivators, and anti-foaming agent. If you walk out to a vehicle on a hot summer day and you start the engine up, turn on the air conditioning, the pressure in the crankcase of the compressor drops dramatically, and a poor quality oil will actually foam up inside the crankcase of the compressor, and the system just simply won't work properly. So there's a lot of science goes into the development of air conditioning compressor oils, and you really need to, there is no such thing as a universal oil. You really need to be using a quality oil when you're, when you're choosing your oil. So the next piece of the puzzle here is we're going to talk about condenser airflow. And for that, I've got another prop ready to go here. And as you can see in this little experiment, we're putting a piece of cardboard in front, we're sliding it down behind the condenser, but in front of the radiator. And this graph here shows us the actual scan data from this particular vehicle. I believe it was a Ford Explorer, if I'm not mistaken. And you can see from this graph here, from the moment we put in the cardboard, within about 20 seconds, air conditioning head pressure has doubled. And then we take out the cardboard and you see the AC head pressure drops dramatically. And the point of this demonstration is that airflow, condenser airflow, can have a dramatic impact. I mean, a really dramatic impact on AC performance. And if you look at the black line, which of course is engine coolant temperature, you see that the coolant temperature actually dropped a tiny amount when we block the airflow. That's because the hot air from the condenser is no longer coursing across the radiator. And so the real takeaway here is, if you're looking at engine coolant temperature as a possible clue or indicator that you have an airflow problem, 9 times out of 10 you're going to come up empty-handed. In other words, an airflow issue will affect air conditioning performance much more quickly than will affect engine coolant. And so I often see, this is a pretty extreme demonstration, but you see shrouds missing, the little draft excluder between the back of the condenser and the front of the radiator. Anything that would affect damaged, broken, missing shrouds and so on, anything that would affect airflow across the condenser will have a dramatic impact on air conditioning performance. Now, what I'm looking at here, this is a vehicle. The compressor and the air conditioning components are related to an 2003, and later Dodge Ram pickup, the Cummins pickup. And what happens on these, we've seen them where we get a lot of tech line calls here. The compressor's been replaced 2, 3, 4 times, and it keeps repeated compressor failure, and the air conditioning never works really well. And the root cause of the deal here usually is this is an electroviscous. It's a computer controlled. The speed is computer controlled, or the electroviscous fan clutch. The viscous fan clutch fails. It may set a trouble code, but it won't turn on the check engine light, and around we go. And so the other issue, of course, this truck also uses what we discussed earlier. It uses a captured orifice tube in the liquid line here. And so if you're not aware of that, people keep replacing the compressor, not understanding that in conjunction with that repair and doing the proper flush, I need to replace, or at least diagnose and confirm that there is no problem with the electroviscous fan clutch. And also, as part of that repair, I need to replace the liquid line with the enclosed orifice tube. So next up here, we're going to talk about recovery, recharging, and recycling. And for that, I'm going to pull in my final demonstration. And so here we have quick. So that this first slide here, I've actually got the component on the cart here. You can see this is, somebody has obviously used sealer in this system. And the point I'm making is before you're about to repair a vehicle, probably the first piece of equipment you're going to connect up maybe is your recovery recycling machine to recover the refrigerant. Well, I'm cautioning before you do that, understand that a lot of folks, you use sealer, you don't know, right? And so you want to be aware, if you draw this sealer into either your refrigerant identifier or your recovery machine, it's going to be a pretty expensive repair bill. So there is a tool out there. This is called a refrigerant identifier. Sorry, it's I take that back. This is a sealant identifier, and not going to get into all the details here, but it's got a little flow meter in here. It comes with a graduated leak, and the whole idea is if the flow drops, you connect it up to the high side of the system. Static is the flow drops, it tells you that the sealer is acting on the restriction, and you've most likely got sealer in the system. So this is a tool for detecting sealer in the system. This is pretty important, folks. You know that this refrigerant's gotten very expensive. People are taking all kinds of shortcuts. Draw sealer into your machine can be a pretty expensive day. The next thing, once I actually sample the check for sealer, the next thing I want to do is use a refrigerant identifier. Here's the latest model that we're looking at here. And you can see that the reason for this is, refrigerant is expensive. 134A, I think, has tripled in price over the past couple of years. YF is $500, $600, $700 for a 10-pound tank. And people are using all kinds of rogue refrigerants in systems. So before you draw that in and contaminate your tank of 134A or YF, it is a good idea to use a refrigerant identifier to confirm that you don't have rogue refrigerant in the system. The other point I want to make about refrigerant identifiers is that they're a great tool for air. If you've got excess air in an air conditioning system, it'll drive the head pressure through the system, stress the compressor, make the compressor knock. A refrigerant identifier will also give you the percentage of air in the system. So it's a great diagnostic tool. Apart from the rogue refrigerant conversation, it's a great diagnostic tool for checking for air in an air conditioning system. So the next piece of the puzzle here, we want to talk about evacuation very quickly before we wrap it up. And you can see here that I've got a manifold gauge set right here, right? And got a manifold gauge set, and this is how in the next slide here, let's take a look at it. This is how I've connected my manifold gauge set to the vehicle. And if we come back here, you see I've teed in a micron vacuum gauge in line with the low side of my manifold gauge set. Or I could do this if I'm using a recovery machine. I can tee in a manifold gauge set, a manifold gauge to the setup as well. Now, where I'm going to use this, I'm going to use this to really enhance my leak checking. If you look at this slide here, you see over on the left-hand side, the conventional gauge is pinned at 30 inches. It looks like it's great vacuum. And on my micron vacuum gauge at about 920 microns, which is decent. I really like to be closer to 500, but it's in the acceptable range. Let's put it that way. In the middle section here, after 10, 15 minutes, you can see that the conventional gauge is still pretty potent, looks good on the, just to the naked eye, but my microns that should be down around 500, 1,000 has bled up to 2,400 and 24,000 microns. And over on the very right picture here, I'm still holding good vacuum on my conventional gauge, but the micron gauge isn't even reading anymore because it needs to see a vacuum of 28.5 inches or better before it will turn on. And my point is, rather than putting the whole system back together and finding a leak later, if I use a micron vacuum gauge while I'm evacuating the system, if that micron vacuum, if I turn the vacuum pump off for a few minutes and I see that micron vacuum bleeding up, that's a dead giveaway that I've got a leak in the system. I'm going to use nitrogen or maybe hydrogen nitrogen forming gas mix. I want to find that leak before I go through all the trouble of evacuating, recharging, and leak checking the system later. I can save myself a bunch of time by using a micron vacuum gauge in conjunction with my manifold gauge set or my recovery machine to monitor vacuum during the evacuation process to see, do I have a slow leak? So So we talked a little bit about we've referenced charge level over the, if you overcharge an air conditioning system, you can potentially end up with this. If you slug a compressor, here's a classic example here. You can't compress a liquid. If you overcharge a system, you get slugging, liquid locking, and now you've damaged the compressor. On the other hand, we explained how the oil drops out. Here's a classic example of, this compressor is bone dry, obviously no lubrication, most likely because the low charge oil dropped out, no lubrication. Here's another example of slugging. This is from an ECV, an electronically controlled compressor. And you can see here that the piston has broken. See the liquid lock, the piston is broken. So that's a little bit about charging. So overcharge, slugging, liquid lock, broken. Undercharged, oil dropout, lack of lubrication. That's the point I want to make here. So let's take a moment here and just talk about leak checking. Don't forget, if you go to our go to 4s.com, click on our YouTube link over on the right-hand side of the screen. We've got a bunch of videos on there about how to, on electronic leak checking and dye leak checking. They're about 10 minutes long. There's some great information in there that will really enhance your leak checking technique, regardless of what particular, whether you prefer electronic or dye. There'll definitely be some good information for you there. So let's get ready to wrap it up here. You've heard this before about checking voltage at the clutch. The point I want to make here, here's a obviously severely burned clutch. Really, every time you do this repair, you need to check for voltage at the clutch. It needs to be within about 1 volt of system voltage. And just to encapsulate it all in one sentence, 1 ohm of unwanted resistance in the clutch circuit will actually reduce the strength of the magnetic field holding the clutch together by about almost half. So that's the importance of doing a good voltage drop check under load at the AC clutch before you run the vehicle to the customer. So we're going to wrap up this conversation with some talking about electronically controlled variable displacement compressors. And I've got one final display card here to talk about that. Get in position, and we'll be with you now in one moment. So you may have noticed that a lot of later model vehicles now are coming with what we call electronically controlled variable displacement compressors. And here's an old school GM V5 compressor here. You can see when I turn it, the pistons are traveling back and forth quite a ways. While this has got an adjustable wobble plate or swash plate in there, if I change the angle of that swash plate, now look at the pistons. They're traveling back hardly anything at all. So in this old school compressor, there was a pneumatic valve. You can actually see a cutaway here in the back of the compressor. And, it monitored low side system pressure, basically evaporator pressure, which is a function of heat load. And if I bleed pressure in and out of the crankcase, I can control the stroke of the compressor here. So that's a pneumatic valve. If I throw away that pneumatic valve and I was to replace it with a computer controlled solenoid, right? We call these ECVs, or electronically controlled variable displacement compressors. If I replace the old pneumatic valve with an electronic solenoid, now the computer can look at high side pressure, ambient temperature, road speed. It can look at a myriad of different inputs to fine-tune the pumping displacement of the compressor. For example, the econ button in the dash prioritizes fuel economy over creature comfort. That will actually affect the command that the computer sends to the solenoid. I'm emphasizing this because there are 2 iterations of this compressor. Most of the early ones were clutchless. Do you see here that when I turn the pulley, the shaft is always turning? So we see these misdiagnosed quite a bit because the technician puts his gauges on there. The high side pressure is abnormally low. The low side pressure is abnormally high, and they think it's a bad compressor. Of course, what we need to check is we need to be sure before condemning this compressor. I would need to know if the solenoid in the rear head here is getting a command from the computer, from the control unit. Now, in later years, they have started putting back. If you look here, it's still an electronically controlled variable displacement, but you can see here that when I turn the pulley, the shaft doesn't the crankshaft doesn't turn. So they've, and later, because they had lubrication issues and different concerns, they have, some manufacturers have started putting pulleys back, conventional clutches back on these computer controlled compressors. So the other thing, important thing to understand about these compressors is that they have, most modern compressors now have what we call oil retention. And there's usually a swirl valve in the discharge port here. It thrusts the oil out against the outside walls of the discharge port. The oil drains back inside the compressor. So a lot more of the oil is retained within the compressor. A challenge in the service world, of course, is if all your oil is retained within the compressor and you add oil on the suction side, add dye on the suction side, it can make dye leak checking much more difficult on oil retention type compressors. So something to keep in mind if you're dealing with a later model vehicle that has the oil in the compressor. The other thing I want to point out here, I may not have referenced it before, is that most modern compressors now have a crankcase. If it's a variable displacement compressor, it's going to have a crankcase, and you can see that it's got a drain plug here. This one's got a drain plug. This one's got a drain plug right here. So if I'm draining this compressor or adding oil to this compressor, I need to be sure to remove the oil. I need to remove oil, or if I'm draining it or adding oil, needs to be added through the drain plug, right? Where if it's an old school, axial GM design compressor like this here, does not have a crankcase, I would be adding the oil or draining oil from the suction port on the compressor. So that just about wraps it up for today. Got some refrigerant news for you before we go. The transition to R1234YF is just about complete. The real differences that you have to watch out for is the oil. The YF systems require an oil. It's still a PAG oil, but it has a heavy-duty additive package to reduce the buildup of acid in the system. Also, the evaporator, I've got one here. They're built to a higher standard. YF evaporator has to have a yellow decal, like you can see here, that says it meets SAJ28 meets SAJ2842 for the flammability concern. And the other piece of the puzzle, of course, is most of these YF systems have that internal heat exchanger that I may have to consider replacing in conjunction with my compressor replacement. And, I do want to emphasize, I'm hearing a lot of anecdotal reports on this, that you remember YF, 134A takes 13 years to break down in the atmosphere. YF breaks down in 11 days. So the consequence of that is if you don't do a good evacuation, trace moisture in the system, you can get very rapid acid buildup in a YF system if you don't follow good hygiene when you're doing a compressor replacement. So you're going to need all new equipment. Don't forget that just part of the AIM Act from back in 2020 there, kind of during the COVID, during the pandemic, R134A is being phased out. It's already, I think, starting October 21, R134A has been cut. Production levels have been cut back to by 10% of 2013 production levels. And over the next 15 years, the plan is to phase it out pretty much all the way. So in other words, by year 2036, they want production of 134A to be only 15% of 2013 levels. So just understand that that's probably going to mean that the cost of R134 is going to become more difficult to find, and obviously its price is probably going to increase. So going to wrap it up today, reminding you, go to 4s.com, click on our YouTube channel, and we have a ton of videos there about dye leak checking, accurate charge level, and so on. A ton of great videos on air conditioning service. And just a quick reminder here: when you go to the to the YouTube, our YouTube channel, click on the video tab there, and then click on, instead of searching up on top where you would kind of normally search, that's going to bring you out to the to all YouTube. If you search on the middle right there, if you type your search term in there, that will search for the content just within our channel. And we've got, as I said, dye leak checking, electronic leak checking, charge level, airflow. There's a ton of great videos there that will help you fix air conditioning issues. So hopefully we brought you something in today's session. Here's a recap of what we covered, and I am going to call it a day right there. Don't forget, our next session is next PowerHour session is May 10th, same time, 11:15 Central, and we will be talking about electronic throttle body diagnosis in our next PowerHour session. Thank you for joining me today.